Balancing chemical equations is perhaps the most important skill that you must have as a chemistry student. Let's correctly balance this equation right here. H2 plus O2 makes water. Now I want to caution you, this is a relatively very easy problem, so pay close attention to both ways that we get the answer, because it's going to help you to not get lost when these balancing problems inevitably get so much harder. Then at the end of the video, we'll summarize with an awesome visual model. There are many different ways that we could go about this, but at its core, it's about achieving two key features. One, that we have the smallest whole number coefficients possible, and two, that we follow the law of conservation. It's always a good first step to use a coefficient of 1 for each molecule and then go from there. And while ones all around are as small as possible, we don't actually follow the law of conservation. Most obviously conservation of atoms, as while we have two H's on each side, we have an uneven number of oxygen atoms. We've got 2 on the left, 1 on the right. And in case you're wondering how we got these atom counts, I multiplied the coefficients with the subscripts. For example, there are 2 hydrogens in a single H2 molecule, so 1 times 2 gives us 2 H's. Here's one of 2 pathways we could go. Because we're an oxygen atom short, we could double the number of water molecules. And that does solve the oxygen problem, but now hydrogen atoms are out of balance. The fates of the atoms, thus H and O in this case, are tied together if they belong to the same molecule. So why don't we change the coefficient for one of the molecules that only has one type of element? If we double the coefficient of H2 from 1 to 2, we double the H's on the left side, and now we have 4 and 4, 2 and 2, and that definitely follows the law of conservation. But does this give us the smallest whole number coefficients? Well, the answer is yes, because there's no way that we could reduce these numbers without yielding fractions or decimals. Here's the other pathway we could have gone, starting from having 1 for each of the coefficients, where because when we manipulated the coefficient of H2O, it had both atoms, let's instead cut the number of O2s in half so we can have 1 and 1. We do that, but unfortunately, while we have the law of conservation followed, because we have 2 and 2, 1 and 1, we don't have the smallest whole number coefficients. We can't have 1/2 of a molecule. So we're just going to scale everything up by 2. Let's bring this all together. How did we get from this all the way down to this? And for brevity's sake, I'm going to use acronyms for each of the criteria, SWNC and LCF. Take note of how each equation has different combinations of coefficients and how that might correspond to the following or not following of the 2 criteria. Part 1 has 2 steps. First, we double the water molecules, then we double the H2 molecules in order to satisfy both criteria. For path 2, we also have 2 steps, but we get there in a different way. We actually satisfy the law of conservation first, but because we have a fraction for a coefficient, we scale everything up and we get the correct answer. Here's a way of viewing both pathways. They both have the same number of steps, but they get there in different ways. Note the similarities and differences.